Alright, so in this video, we're going to be going over something called the logistic model. So this is a way to address some of the problems with some of the differential equation models we've looked at so far. So specifically, the logistic model is often seen with regards to population growth. So one model we already saw for the growth of a population of some sort of animal or something like that was the exponential growth model, which was y prime equals some constant times y. And if we sort of approach the problem naively, this makes some sense. We think of y as the population of some animal. Then this is saying that how quickly that population grows is going to be proportional to the amount of the animal that's around. And that makes some sense because if there's more of the animal, there's more of them that can reproduce, and so they should increase their population at a quicker rate. But some things are not realistic about this model because, for example, if the population starts off positive, then the solutions will do something like this. They just keep growing forever. And this isn't realistic because if you think about in the real world, obviously a population is not going to grow indefinitely. That's not what I wanted to say. So the resources that are available to this creature are going to be limited, right? You know, it's going to have limited food supply, limited water, and so on. And so if there's too many of this creature around, the environment just won't be able to support them. And that means that this exponential growth model is really unrealistic at some point because it's predicting that the population will just keep growing forever and growing faster and faster and faster, when we know that that definitely can't happen. So the logistic model is a way to sort of get around this by introducing what's known as a carrying capacity. So the logistic model says that if P is the population of our creature, then P prime is equal to Kp times 1 minus P over L. So L is a constant known as the carrying capacity. And we'll see in a little bit why this is an important feature in this model. The K is just some constant, sort of like we had in this first one. So if we try to solve this with separation of variables, it is a separable equation, but we run into some problems because we have to take the antiderivative of P times 1 minus P divided by L. While it's possible to find that antiderivative, it's not something that we've really covered how to do in this class. So for the moment, I'm just going to assume, for the sake of our discussion, that we cannot find an analytical solution to this equation. In class, when I have a bit more time, I'll show you what the solution is, and then once you know the solution, you can plug it in and verify that it works. But it's actually not all that interesting. We can find out the most important features of this model without knowing the solution at all. And that's what I'd like to focus on how to do. So the first thing we need to do is find what are the equilibrium solutions to this equation. So remember, an equilibrium solution occurs when P prime is equal to 0. So that means this product, Kp times 1 minus P over L, is equal to 0. That gives us two choices. Either P is equal to 0 or P is equal to L. I'm assuming, of course, that this constant K is not equal to 0 because then it would just be a trivial problem. So we have these two possibilities. So if we start off with 0 population, then we'll stay at 0 forever. That makes sense. But also if we start off with L, then we'll stay at L forever. This is a new feature that the old exponential growth model did not have. So if we take a look at the TP plane, there's going to be a horizontal line at a height of end. The solutions to the equation, if they start on L, then they will stay there forever, right? This is an equilibrium solution. Now the question is, how do the solutions behave nearby this equilibrium solution? Well, if P is greater than L, then we have that 1 minus P divided by L is less than 0. And that means P prime is less than 0. So P is decreasing. And we can also find if 0 is less than P is less than L, then this quantity is positive. So that means P prime has to be positive, right? Because P is always positive, it's the population of some creature. And so what determines the sign of the derivative is just this piece here. So that means that if we're up in this region up here, then the function is going to be decreasing. If we're in this region down here, the function is going to be increasing. So the solutions end up looking sort of like this. And this inflection point here occurs exactly at L divided by 2. So half the carrying capacity. If you start above that, then you just have this piece here where it's concave down. So depending on your initial condition, you get different behaviors for the solution. If P0 is greater than L, the population decreases. But if P0 is less than L, the population will increase, but only up to the carrying capacity. So what this tells us is that no matter what, in the long term, our population is going to level out to the carrying capacity. The size of the population is initially large, and that means there's more of the animal than the environment can support, and they'll start to die out. If the population is small, then they'll increase up to the level of the population, or that the environment can support, which is L. So that's why we call L the carrying capacity. In this case, we can see that L is a stable equilibrium for this equation. So this makes the logistic model useful because it allows us to get a more realistic equation to represent population growth. And so in the next video, we'll see how we can use similar ideas to this, how we analyze the logistic model to analyze pretty much any differential equation. So this is known as qualitative analysis, and we'll discuss it a lot more in the next video.